Hello, 6.2, day one, approximating areas with Riemann sums. So we're going to find the approximate area under a curve down to the x-axis using rectangles to approximate the curved area. And that is called using Riemann sums. Riemann, it was a mathematician who first discovered this method. So what we left off yesterday or last time was that we had a particle moving along a straight path. The graph here, there's another typo, particle Q moves along a straight path with the graph of the velocity at time t. So there shouldn't be a end of a sentence there, shown to the left. And remember that to find the position or total distance that the particle traveled, we want the area under this curve because we want to multiply time times rate. Remember, rate is velocity. So distance would equal rate times time. And that's basically finding the area under this curve down to the x-axis. But this area has a weird shape, so we can't use geometry to find that area. We could approximate it by counting up the boxes, which we did yesterday, but still that's not a very close approximation. So we're going to approximate it even better by using rectangles, which are called Riemann. It's a Riemann sum because we're going to sum up the areas of the rectangle. So we're going to make a rectangle for as many as we want. Let's say we're just going to make two rectangles, and we just make a rectangle here where the right corner touches the curve, and then another rectangle here where this right corner touches the curve. So a very rough estimate would be whatever this y value is on the right side, it would be the height, and whatever this y value is on the right side would be the height, and then the rectangle's width would be 1. So it would be 1 times the height plus 1 times the height. So those two rectangles we would add up. And then later we're going to talk about using trapezoids instead, because you can see that a trapezoid would be even a better approximation because it wouldn't have all this extra area left off there. So we're going to start with rectangles, and that is Riemann sums and some decisions we have to make. Oh, forgot, I was going to talk about Riemann. So Georg Friedrich Bernhard Riemann, German mathematician, did his most famous work in non-Euclidean geometry. So the geometry you've learned about is mostly Euclidean geometry. Differential equations, which we know about in calculus, and number theory, which you probably haven't taken any courses in, but that's like with the intersection and union and a whole bunch of other things. So you've done a little introductory level with number theory. It was Riemann's results in physics and mathematics that formed the structure on which Einstein's theory of relativity is based. So he was pretty important to the basis of calculus and math and physics in general. All right, so to approximate the area under a curve using rectangles, we have to decide a few things in advance. How many rectangles are we going to use? And sometimes they will tell you that. They're called subintervals. So subintervals are how many rectangles we're going to use, and they will usually tell you in the problem how many to use. And then how will we determine the height of each rectangle? The height of the rectangle will be based on the corner of the rectangle that hits the graph. So if the left corner of the rectangle hits the graph, then that will be the height, and it's the y value of whatever, let's say this is the point C. Whatever that y value is at C is the height at that x value of C. That's the height of the rectangle. So it might be the left endpoint, or maybe it's the midpoint of the rectangle. So if this is C and this is D, we'd add them together and divide by 2 to get the midpoint, and then find the y value at that midpoint to find the height, or the right endpoint. So maybe we'll have the right corner of the interval. And so if this is D, then f of D would be the height. So you're going to plug in the x value either on the left side, the right side, or the middle of the rectangle to get the height of each rectangle. And then all of the rectangles may have the same width, or Riemann said they don't even have to have all the same width. But when we are doing it with an equation, given an equation, we will have all of our rectangles have the same width. If we're doing a table, then we may have rectangles with different widths. So that is flexible. So let's do an example of finding the approximate area under a curve. We're just gonna find the right one here. So let's not do both left and right. But we could find 2 approximations, or 3. We could do the midpoint too. Find the approximation of the area using the right endpoint of the region lying between the graph of negative x squared plus 5, and I've got part of that graph here. It's this curve. This obviously goes down more, and then over here would eventually curve down later. Between x equals 0, which is this line, and x equals 2, which is this line, and the x-axis. So just this region that's kind of filled with rectangles, but we would really like the area including all of this empty space too. But we're just going to approximate it using those 5 rectangles. So 5 subintervals, that means 5 rectangles, and they all have the same width. So our first thing is to find the width of each rectangle. So you subtract the 2 endpoints, and you divide by how many rectangles there are. So each rectangle has a width of 2/5. So this x value is 2/5. This x value is 4/5. This x value is 6/5. And you need these x values because 10/5, which is 2. Because those are the ones you plug into the function to find the height of each rectangle. So I've determined the value of each right endpoint. It's b minus a, so we call this a and this b. The left endpoint is a and the right endpoint is b. So it's b minus a divided by how many rectangles you have. So the formula, if you like formulas, is b minus a over n. N is the number of rectangles or number of, not equal to. Not equal to, I want it equal to. N is equal to the number of rectangles or the number of sub-intervals, which is the same. So to determine the value of each right endpoint, you do b minus a over n times the number that you're on. Like if we're on the first rectangle, it's b minus a times over n times 1. If we're on the second rectangle, it's b minus a over n times 2. So it's times I, which is the counter of whichever rectangle. And if the left endpoint is not 0, you'd have to add that on. So let's determine the height of each rectangle. We're going to do f of each endpoint. So this looks pretty complicated, but really we're just going to do f of 2/5, and then f of 4/5, and then f of 6/5, f of 8/5, and f of 2 to get all of those heights. So you can use a calculator for calculating the heights. I would recommend going to y equals and typing in negative x squared plus 5, and then go back to your home screen and do vars, y-vars function, y1, and then parentheses 2/5. So you have y1 of 2/5, and you get 4.84. And then do the same thing, y1 of 4/5, and you get 4.36. So these are the heights of the rectangles. And then 6/5, or you can go to your table, but you'd have to set up what the table is counting by as fifths, which is a little more complicated. And then 8/5, and then 2. You could probably do that one in your head, right? So let's just see how the heights are looking. 4.84, that makes sense because it's a little bit below 5. The next one looks like it's about between 4 and 5, so 4.36 makes sense. Just making sure I've done my math correctly. F of 6/5 is about halfway between 3 and 4. F of 8/5 is a little bit higher than 2, and F of 2 is at 1. So those are the heights. And then you want to find the area of each rectangle, and the width of each rectangle is 2/5. So a rectangle number 1, the area is going to be 2/5 times 4.84, base times height. Rectangle number 2 is 2/5. So the width of each rectangle is always the same in this case, 4.36. And I'm going to add all these answers together. Just need a little more room here. So then I have 2/5 times 3.562 and 2/5 times 2.44 and 2/5 times 1. And I'm going to add them all up. So another way to do that is just 2/5 times, and then you can add up your answers if you want, because they're all being multiplied by 2/5. You can multiply the whole answer. Oops, I forgot the +1. It's just the distributive property helping us out there. All right, so 4.84 plus 4.36 plus 3.562 plus 2.44 plus 1, and then all of that times 2/5. About 6.4808, and we want it to 3 decimals, so 6.480 is fine, or 6.481 is fine. So that's just an approximate area under the curve between 0 and 2 down to the x-axis. We can get more accurate if we used more rectangles, because we'd have less open space here, right? And if we did a left, we did the one where the left rectangles were on the curve, left side of the rectangles were on the curve, then we'd get a different approximation, but it would be around 6.481. All right, let's try, oh, I forgot, we should talk about the notation. So Riemann came up with a notation that instead of using the words, because you know mathematicians want to put everything down to notation, instead of saying, what's the area under the curve down to the x-axis between these two values, he used a symbol. So he used the symbol of the integral, which we've learned about already, but we've used it for something different. So he used it for the area under the curve of -x² + 5 between 0 and 2. So it still has a dx, it still has the integral, and we will find out there's a connection between them later, but this is called a definite integral because it's got numbers. We haven't used numbers there yet. So right now all you need to know is this means find the area between the graph of -x² + 5 and the x-axis and between 0 and 2. So that area. Okay, that's what we know so far. So let's use a left Riemann sum. So we're having the left side of our rectangle touch the curve with 2 equal subintervals. So we're doing 2 equal rectangles, 2 equal bases. You know, the rectangle width is the same, to approximate the area between 0.5t² + 1 and the x-axis between 0 and 2. So this is how Riemann would notate that, the integral, and that's how we are. I just keep saying Riemann because he's the one who first came up with it. But we are going to use this symbol, this integral symbol, to mean find the area under the curve, and then using rectangles. So the left corner is touching, so there's one, and then here is rectangle number 2. So the left corner goes as high as the curve allows it to. It will never go above the curve. So you see we have a lot of empty space here that we're not counting. So can you determine if this approximation will be too high or too low? We'll talk about that in another lesson, but I think you can be able to tell what it is. So what we have to do is find the width of each rectangle. So we're going 2 minus 0 over 2, b minus a over n. That's 1. That was pretty obvious. That's the width of each rectangle, but sometimes they're more complicated. Like the last one, it's going to be, the last one we just did was 2/5. All right, then we need to find the x values. So our left side is counted this time. So our first x value is 0, and then our second x value is 1. And you can call it x sub 1, x sub 2 if you want. And so I want the height at each of those. So I'm going to do 0.5 times 0² + 1 to get the height, and then 0.5 times 1² + 1 to get the height. So that height is 1, and this height is 1.5. So then I want to find the area of each rectangle. So I take the width, which is 1, times the height, width, which is 1 times the height, and get those areas. and I add them up. So the approximate area is about 2.5 units, but we can see that it's actually lower than what it should be because we're missing all of this area here. Let's do a right Riemann sum for this exact one. So the rectangles, again, we have 2. So the width is 2 minus 0 over 2. So the width again is 1. So the rectangle number 1 will go from 0 to 1, and we want the right corner to be on the curve. So our first value is 1 and our second is 2. The height is 0.5 times 1 squared plus 1 and 0.5 times 2 squared plus 1. So the area, the height of this would be 1.5, and the height of this, 4 times 0.5 is 2, so 3. And that corresponds with what you see on the graph there. And the area of each rectangle then would be 1 times 1.5, which is 1.5, and 1.3, which is 3. And you add them up. And so this approximate area is 4.5, which is much higher than what we had before, but you can see it's counting all of this extra area here. So this is an over approximation. And we could use the midpoint too. So if we wanted to do the midpoint of the rectangle on the curve, the midpoint between 0 and 1 would be 0.5. So then our rectangle, oops, that's going down, would have a height of whatever the y value is at 0.5. And then this one, the y value at 0.5 is here. So our rectangle would be that high. And then you would just do 1 times that height and 1 times that height and add them up. So midpoint is kind of the same. You just have different numbers to plug in. What would happen with our approximated areas if we used more rectangles? So there is a Geogebra animation that we're going to look at. I'm hoping you can see this. I'm not sure if you can. I might have to splice it in. All right, so if we used more rectangles, you see this area, this was the negative x squared plus 5, one was 6.48. If we use more rectangles, the area gets bigger and we have less and less empty space that we're not counting. The more rectangles we use, remember, just going from 0 to 2, so you don't count this little empty space by the x-axis. Just look at the rectangles, and they're skinnier and skinnier, so they're having less and less little empty space in between. So the more rectangles we use, the closer our approximation is to actual, because it's almost making a full curve. So the more rectangles, the better. It gets a better approximation to the actual value. Hopefully that showed up for you. If not, I'll splice it in. All right. Then let's do a real life example. Tiffany posts a picture of her posing with Sir Isaac from the pop group Sir Isaac and the Newtones on her Instagram at 9 a.m. The rate that her followers view her picture is modeled with selected values shown in the table above. So this time we're not given an equation, we're given a table of values. The rate that her followers view her picture is modeled with selected values shown in the table above, where t equals 0 represents 9 a.m. And the rate is measured in people per hour. So this is a rate. It's a p prime. That's the rate. And this is time. So for us to find the amount of people that have viewed her Instagram post, we're going to multiply rate times time. So use a right Riemann sum. They're telling us which one to use, and we're going to do 3 subintervals to approximate the area, p prime of t, and the t-axis from 0 to 5. So from 9 a.m. to 5 hours later, which would be 2 p.m. Include units of measure with your answer, and what does this answer represent in the context of the problem? So let's first talk about the context of the problem. If you're integrating the rate, basically you're multiplying rate times time, the rate of the number of people viewing her post would then, we've got to use the noun, the units, and the time when you're describing what it represents in the context of the problem. So the problem has to be, the noun would be like, what thing are you talking about? Don't just say the answer is 6 in 5 hours. Whatever, if your answer is 6, you have to say 6 what? So our answer is going to be the number of people, that's our noun, viewing her post. Or we could say the total number of people would be even better. Total number of people viewing her post. The units, so people is our units. Total is our noun. In 5 hours. Or in those 5 hours, we should say. Between 9 and... So say what it is, what the units are, and what time interval is being discussed here. So always include all 3 of those. That include the nut of the answer. All right, let's find the answer now. So we want 3 subintervals. So we're going to go 5 minus 0 and divide by 3. So each rectangle has a width of 5/3. Oh, we have to use the table though. So never mind. That's different. We have to use the table. So we want to break our table up into 3 subintervals. So like 0 to 4, 4 to 6, 6 to 12, or can we break it up into 3 equal subintervals? Does it say how we have to break it up? Sometimes it tells you like to use, we're only going from 0 to 5, right? So we've got to use those 3 that are given to us. So 0 to 2, 2 to 4, and 4 to 5, because we only go from 0 to 5. So the 3 subintervals we have are 0 to 2 and then 2 to 4. So those 2 are both the same width. They are 2 units wide. And then from 4 to 5 is only 1 hour wide. So if we're doing right Riemann sum, that means the right side. So from this interval from 0 to 2, we're going to use the right side of it, which is a height of 30. If you want to picture it graphed, 0.41 would be up here, and then 2.30 would be down here. And so what we're doing is saying we're using the right side. So that's a height of 30 and the width of 2. And then for the next one, we're going from 2 to 4. It has a height of 54 on the right side. So it's going to be up here. So it's a height of 54, and then the width is still 2. And then from 4 to 5, which is skinnier, width is 1, it's a height of 26 on the right side. So you look at the right side of the interval's y value. So this would be 26 times 1, which is just 26. So we have 60, 30 times 2, plus 54 times 2, which is 108, plus 26. And then you add those up. So there's less calculating to do when you have a table of values. So the approximate area, using this notation that Riemann helped us with, is 194 total people viewing her post in the 5 hours from 9 a.m. to 2 p.m. So make sure you include all of that in your answer. Let's do a left Riemann sum with 4 subintervals from 4 to 12. So it's the same setup, different question. Write the notation. Okay, let's start with that. So we're going from 4 to 12, and we're integrating the rate, or we're doing the area under the rate of people per hour. All right, let's do a left Riemann sum with 4 subintervals from 4 to 12. So we're going from 4 to 12. So we're going to use 1, 2, 3, 4 intervals. So 4 to 5 is one of them, 5 to 6 is another, 6 to 9, and 9 to 12. So we're using the left side of the rectangle. So the first rectangle, number 1, will have a height of 54 and a width of 1. That's the difference from 4 to 5. Plus, then rectangle number 2 goes from 5 to 6, and its height is the left side, so 26 times 1. The width of the rectangle again is from 5 to 6, which is 1. And then from 6 to 9 has a height of 21 because we use the left side, but 6 to 9 is 3 wide. And then from 9 to 12, our height is 44 using the left side of the interval times a height of 3 or width of 3. So this notation or this work where you write down what you're multiplying together is vital on these questions. They will expect you to show the work for this as a setup of your answer. So 54 plus 26 plus 63 plus 132 So unless I made a silly error, that's your answer for the approximate number of people. I should do squiggly equal sign. The approximate number of people including units and the noun, the total number of people. People is the units. The total is the noun. Watched her post from t equals 4 to 12. You don't even have to say like the actual time, like 9. If 9 a.m. is 0, then 4 would be 1 p.m. You don't even have to say that. You can just say from t equals 4 to 12. All right, let's try another one. Same thing, but we're doing a midpoint Riemann sum from 0 to 12 with 3 subintervals. So that's 0 to 4, because 2 is going to be our midpoint. And then 4 to 6, because 5 is going to be our midpoint. And then 6 to 9. So you divide it up evenly according to what the table has. And then your midpoint would be the one in the middle of each of those intervals. So you divide up your 12 into 3 subintervals. So you're going to go from 0 to 4, 4 to 6, and 6 to 12. And our integral notation would be 0 to 12. And it's an approximation. All right, midpoint. So 2, the height is 30. So 30 times, and the width from 0 to 4 is 4. The height of the middle rectangle, which goes between 4 and 6, has a height of 26, which is from 4 to 6, so that's 2 wide. And the third rectangle has a height of 44 from the midpoint, and it has a width of 3. From 6 to 9 is 3. So 120 plus 52 plus, again, 132. So that's 304. So it's approximately 304 people total, or people viewed. There you go. Your homework is 2 assignments. There's one on Delta Math, and then there's a worksheet in Schoology that you're going to do and then upload. Make sure you do them both. Have a great day.